Welcome to this video on graphing without a calculator. Before we can get into the video, this video involves natural logarithms, and it would be worth our time to do a quick review before we really get into the heart of the graphing without a calculator issue. Some reminders. The natural logarithm of 0 doesn't exist. The natural logarithm of 1 is 0. The natural log of e is 1. And if you pick a number between 0 and 1, such as 0.6, its natural log will be a negative number. If you pick a number between 1 and e, because the natural log is an increasing function, then it must be between 0 and 1. And if you pick a number larger than e, the natural log of that number will be greater than 1. And furthermore, the bigger x gets, the bigger the natural log gets. If all of this sounds unfamiliar or it's been a while since you've worked with natural logarithms, you may want to pause the video, check out another one on natural logarithms before we proceed. Technically, graphing without a calculator is not about natural logarithms per se, but they do arise quite frequently in this subject. So a familiarity with them will be very, very helpful to you. Another thing that we have to analyze before we can really get into the video in any great detail is to tell whether a quantity is positive or negative without the use of a calculator. If I were to ask, is this quantity positive or negative? Most students would say that there's no way to tell without a calculator. That's not entirely true, although I did work this out on a calculator and I got a negative result. Remember that for later. It turns out, while I couldn't have found a 4 decimal place accuracy without a calculator, I can still tell whether this is a positive or negative quantity without a calculator. See if you can follow this logic. Here's the expression we're interested in. The natural log of 2. I don't really know what that is without a calculator. But because 2 is between 1 and e, then the natural log of 2 must be a number between 0 and 1. That much I know. And so my numerator is essentially 1 minus a number that's between 0 and 1. You shouldn't need a calculator to know that 1 minus a number between 0 and 1 is positive. So we know that the numerator of this fraction, whatever it may work out to in decimal form, is a positive number. Now let's look at the denominator. Radical 10. I don't know exactly what that is without a calculator, but I know that radical 10 has to be bigger than 3. After all, radical 9 is 3, so radical 10 must be bigger than 3 since radical is an increasing function. So my denominator is essentially 3 minus something bigger than 3. Well, you don't need a calculator to know that 3 minus something bigger than 3 is negative. So with no calculator at all, I've determined that this fraction, if put in decimal form, would end up being a positive divided by a negative. But we know that any positive divided by any negative is a negative. So this quantity, therefore, must be negative, as the calculator showed. There is lots of this logic in the video, and it would be a distraction if every time I used it, I paused and analyzed each individual portion of an expression. So you'll hear me say in this video quite often, oh, this quantity is positive or this quantity is negative. This is the kind of reasoning that's behind that logic. But why do we even bother to graph without a calculator? We have apps that can graph things for us. Is there any reason to anymore? Well, there is a tremendous reason to, because doing so trains us to think about how changes in one quantity affect another quantity. And that basic scientific thinking is necessary if we're going to use mathematics and science together to progress and solve real-life problems. So this is a great training exercise to graph without a calculator, even though we have apps that can graph for us. basic question that we try to answer when graphing without a calculator is, as x ranges from negative infinity to infinity, what's happening to y throughout that time? And that thought process is very valuable, as it turns out. So one more thing before we get into the meat of the video, some reminders from algebra. In this video, we'll discuss x-intercepts. Quick reminder, x-intercepts are found by setting y equal to 0. For example, if we wanted to know the x-intercepts of this function, we would set 0 equal to y and solve for x. Here's another quick reminder from your algebra past. Notice the bottom equation here says fraction equals 0. A fraction can only equal 0 when the top is 0. So we can see here that x equals 2 would be an x-intercept, and in fact the only x-intercept to this function. Here's a second reminder from algebra, y-intercept. The y-intercept of a function is found by setting x equal to 0. For example, if we wanted the y-intercept of this, we would plug in 0 for x and solve for y, thereby giving us the y-intercept. That shouldn't sound new to you, but it comes up a lot in this video, so it's worth mentioning here. And our third and final reminder from algebra, vertical asymptotes. These are vertical lines that the graph doesn't cross, but approaches, either up towards positive infinity or down towards negative infinity in the y sense. More on that later if it's been a while since you've heard of a vertical asymptote, but what's worth knowing is vertical asymptotes are caused either by division by 0 or by taking the logarithm of 0. For example, if we were graphing this function, x being 2 would force us to have the logarithm of 0 in our expression. The logarithm of 0 doesn't exist, and about 98% of the time, this will cause a vertical asymptote in your graph. And so therefore, x equals 2 would be such an asymptote. Here's another example. If we wanted the vertical asymptote in this function, notice it has no logarithm, but we would have x equals 3 as a vertical asymptote, because if x were 3, that would cause the function to involve division by 0. And about 98% of the time, that causes a vertical asymptote. So with all those algebra reminders behind us, let's look at an actual problem. Here's the first of 5 functions we're going to graph without a calculator. I'm going to run through the key features of the graph and see what I can deduce about it. The first key feature worth looking at is the x-intercept of this function. This function can only have a 0 y value when the numerator is 0. That can only happen when x is 2. So I've deduced that 2 is an intercept to this graph, and further, it's the only x-intercept to this graph. Now, whenever I like to find an x-intercept, or whenever I find an x-intercept, I prefer to follow up with a little bit of investigation. And what I do is I will plug in a number slightly to the left of that intercept and slightly to the right of that intercept. And that will give me a sense of the function's behavior near to. Behavior just means where the graph is. So I'm going to plug in something slightly to the left of 2 into this function. Now, I recommend pausing the video and convincing yourself that this is a positive number. I don't know exactly what this function works out to when x is 1.9, but I know it's a positive number for sure, just by looking at the expression and doing a little bit of analysis. So now that I've plugged in a number slightly to the left of 2, let's pick a number just a bit to the right of 2, such as 2.1. You can see by looking at this expression that it's going to be a positive divided by a positive, or a positive. Now, what do these two positive y values tell us about the function? They tell us where the graph is relative to the x-axis. In other words, because the function has a positive value to the left of 2, it's going to be slightly above the x-axis when x is 1.9. Likewise, it's going to be slightly above the x-axis when x is 2.1. And that tells me that the behavior near 2 is as shown in the graph here. I don't know that it looks exactly like that, but I've drawn this to represent that on either side of 2, the function is positive. And that gives me a sense of where that portion of the graph is and will be going as we stretch out towards other parts of the graph. The second key feature I like to find is the y-intercept. The y-intercept is found by plugging in 0 for x, and this quantity works out to be positive 1/3. Notice the y-axis. I can therefore conclude that I have a y-intercept of 1/3. By the way, one thing that I recommend before we go any further in this problem, what I recommend when sketching the graph of a function is that you don't worry too much about the scaling of it. 1/3 is probably a lot lower or closer to the origin than that, based on the scaling of this graph. But sketches of graphs don't really rely on scaling. It kind of defeats the purpose, in fact, to have a scaled graph, because the very exercise of graphing without a calculator is to get a rough idea of where the function is going, not a precise one. So don't worry about scaling, in other words, where exactly positive 1/3 should be. The third thing I like to look at is I like to look for vertical asymptotes. Vertical asymptotes occur in two cases: one, when the argument of a logarithm is 0, or 2, when the denominator is 0. Well, there are no logarithms here, so the denominator would be 0 whenever x is -6. And therefore, x equals -6 is a vertical asymptote to this function. Now notice what I'm doing here. I'm finding important key features of the function and building it together, hoping in the end to put it together into one comprehensive sketch. But let's keep building our clues here. Whenever I find a vertical asymptote, the very next thing I ask myself is, what is the behavior to the immediate left of that asymptote and to the immediate right? Let's start with the immediate left. To get a sense of what the function is doing slightly to the left of 6, -6, excuse me, why don't we plug in -6.1? Well, some analysis here would show, even without a calculator, that this is a negative quantity, essentially because it ends up being a positive divided by a negative. Now, what does this mean exactly? It means when x is -6.1, y is some negative number. We don't know what number, but we know it's going to be negative. And therefore, watch the graph here. I can conclude that my graph will be going downward towards the asymptote there in the negative direction. I know that because when x is -6.1, y is a negative number, and therefore the graph must be going down that way. Graphs always approach their vertical asymptotes, so it either has to approach in an upward or a downward fashion. And in this case, because of the negative quantity there, it's going to be approaching in a downward fashion. Now that I've examined the behavior of the graph to the left of -6, let's examine it to the right of -6. What's slightly to the right of -6? How about -5.9? Now, if we plug in -5.9 to this function, we're going to get a positive divided by a positive, which is a positive. What does that tell me? That tells me when x is -5.9, the y value is positive. That means that the corresponding point is above the x-axis. And therefore, on the right side of my asymptote, watch the graph here, the graph must be approaching it in an upward fashion. So I've now gone through 3 of the key features, and I have a general sense of where this graph is going. And notice I haven't used a calculator. The fourth thing that I like to do when analyzing a graph is to look at its so-called end behavior. Let's start with the left end of the graph. We'll get to the right end in just a moment. I like to know when x becomes a very large negative number, if you will, like negative 1,000 or negative 1 million. As we go to the far, far reaches of the left side of this graph, what's happening to the function? Well, one thing that I like to do to imagine that left end behaviors, I like to plug in negative 1,000 to the function. Well, there's nothing special about negative 1,000. We're really asking a more general question here. What's happening to y as x becomes very, very negative? But negative 1,000 gives me a good sense of what's going on, so I like to use that as my example. Now, this quantity here that you see is going to be a positive divided by a negative, and therefore it's going to be a negative. But it's going to be very, very close to 1. Doesn't this, after all, work out to 1,002 over negative 994? Well, how many times does 994 go into 1,002? Pretty much exactly once, or almost once. So my conclusion here is that the left end behavior is as follows. As x approaches negative infinity, or goes further and further to the left, y is going to be getting closer and closer to negative 1. Imagine it another way. This graph contains a point, negative 1,000, comma, something very close to negative 1. And if you were to plot that point, you would be convinced that as x approaches negative infinity, the graph, or the y values, are approaching negative 1. And I've shown that graphically here. The other end behavior, of course, is the one on the right. So we now want to ask the question, what's happening to the graph as x gets bigger and bigger and bigger, or as x approaches infinity? Well, again, we can't plug in infinity, but we can plug in 1,000 to get a general sense of what's happening. And if you plug in 1,000 here, you'll get 998 over 1,006. That too is very, very close to 1, although this particular one is positive. And by just plugging in 1,000, again, there's nothing special about that, but I've convinced myself that the y value is so incredibly close to 1 that y must be approaching 1 as x approaches infinity. And therefore my conclusion is that the graph is approaching the horizontal line y equals 1. In a sense, we found two horizontal asymptotes to this graph, one on the left and one on the right. Not all graphs have horizontal asymptotes, but this particular one has two. So now I'm sort of at the end of my clue finding, if you will. I found a y-intercept, I found an x-intercept, I found the behavior near the x-intercept. I found a vertical asymptote and the behavior on either side of it. And I found the far left and far right end behaviors of the graph as well. So what's happening everywhere else? Well, for the purposes of sketching, we don't really care. So all you need to do at this point is connect up all the things, you may see them in red here, but connect up all the key components of the graph that we've already deduced without a calculator, and you have a sketch. What happens if you don't connect them in exactly the right way? Nobody cares about precision. We're looking for a general sketch of the graph. So ultimately, there it is. That's the general sketch of this graph. Now, because I used a computer to generate this image, it's actually a very precise, to some extent, a precise graph. But you wouldn't expect yours that you would draw by hand to be so precise. Before we go to the next problem, there's something that I need to warn you about from your math past. There's a very good chance that one of your teachers would ask you, when drawing a graph by hand without graph paper, to make tick marks on the x and y axis. Don't do that at this level of mathematics. There's no reason for me to have bunch of tick marks floating around on the axis, because when we sketch a graph, we only want the most relevant information shown. So notice that things that are labeled on my axis are things that are pertinent to this particular graph. And to put in additional tick marks or additional information would really be a distraction from the point. So we want to take a minimalist view here and not have a bunch of extraneous information cluttering up the key features that we see in front of us. Now let's take a look at our second of 5 examples. Here we're going to graph y equals the natural log of x minus 5. Let's run through the same 5 key features and see what we can discover. First, the x-intercepts. X-intercepts occur whenever the function is set to 0, but the solution to this equation is clearly 6, because 6 minus 5 is 1, and the natural log of 1 is 0. And so I know that I have an intercept, an x-intercept of 6. And whenever I find an x-intercept, again, I like to plug in a number just to the left and just to the right of it. So I'm going to plug in 5.9. 5.9 minus 5 is 0.9. And the natural logarithm of 0.9 is a negative number. I know that because 0.9 is between 0 and 1, and that's just something I know about natural logarithms. On the other side of the intercept, slightly to the right, let's say at 6.1, we get a positive quantity because 6.1 minus 5 is 1.1, and the natural log of anything between 1 and e is between 0 and 1, and specifically positive. So knowing information about the natural logarithm is important here. But putting that aside for the moment, I don't want you to lose the bigger picture. I've plugged in a number to the left of 6 and to the right of 6 and gotten a negative and positive result. That means that my graph is below the x-axis at 5.9 and above the x-axis at 6.1. What does that tell me about the behavior of the graph near 6? Watch the graph. The graph must be like that. I've drawn a straight line here. I'm in no means meaning to imply that the function is linear at 6. But I do know that it's going to be below and above the x-axis as shown based on my analysis. My second clue is the y-intercept. Y-intercepts are found when x is 0. 0 minus 5 is negative 5, and the logarithm of a negative number doesn't exist, not in the real number sense anyways. So my conclusion here is that there is no y-intercept for this particular graph. Thirdly, let's look at our vertical asymptotes. Vertical asymptotes can occur when you have an argument of a logarithm being 0. So in this case, at 5. And whenever I find a vertical asymptote, I like to plug in a number just to the left and just to the right of it to get a sense of the behavior of the graph. So we'll start by plugging in 4.9 and see what happens. 4.9 minus 5 is a negative number. Natural log of a negative number does not exist. And therefore, there's no graph. The graph doesn't exist when x is 4.9. In fact, if you think about it, if x is any number to the left of or less than 5, this function will have a negative argument and therefore won't exist in the real number world. So there is no graph to the left of that vertical asymptote. Let's plug in the number slightly to the right of that. 5.1 minus 5 is 0.1. The natural log of 0.1 is a negative. That's a fact about natural logarithms. And therefore, because the function is negative there, it must approach the asymptote in a negative fashion. Watching the graph, we can conclude that the graph is approaching the asymptote that way. Let me say this another way. When x is 5.1, y is some negative number. Therefore, this graph must pass through 5.1, comma, some negative number. That leads me to conclude that the graph has to be approaching the asymptote as shown there. As far as our left end behavior goes, let's plug in a -1,000, but that doesn't get us very far. It just reminds us that when x is negative, the argument's negative and the logarithm does not exist. Again, we've already discussed that there's no graph on the left side, so let's move on to the right end behavior by plugging in positive 1,000 and trying to analyze what we might get. When x is 1,000, y is the natural log of 995. That convinces me that as x approaches infinity, y is going to approach infinity. Reason? The bigger x gets, the bigger the natural log gets. That's just a fact about the natural logarithm. So this graph is going to be approaching y equals infinity as x gets further and further to the right. That tells me that the graph is going to be something like that. By the way, it's just an interesting side note that while it is true that natural logarithm gets bigger and bigger, it gets bigger very slowly. For example, I'm holding a calculator right now, and the natural log of 995 is about 6.9. So imagine this. This graph passes through the point 1,000, 6.9. Imagine where that is. And you can see what a slow growing graph a logarithm can be. Nonetheless, we've analyzed all 5 key components of the graph. Now it's just a matter of drawing something that's consistent with all of them. And we're not looking for excellent scaling here, but just some general sketch of the graph. There is what the graph looks like for the natural log of x minus 5. Here's our third example of 5. I've drawn mostly quadrant 1 and 1 and 4, because that's where the majority of the interesting information is. Let's go into our 5 elements of the graph. First, our x-intercepts occur whenever the numerator is 0 if we have a fraction, and so we have an x-intercept at 5. Okay, let's analyze the graph slightly to the left or slightly to the right of 5. We'll try 4.9 first. Convince yourself that this is a negative quantity. The numerator is negative. The denominator has to be positive because the square root of 4.9 has to be 2 point something, and 3 minus 2 point something is a positive number. Now, slightly to the right of 5, convince yourself that this is a positive quantity. It ends up being a positive divided by a positive. So because my graph is negative and positive on the left and right side of the intercept respectively, then the graph must be passing through the intercept as shown there. And again, I don't mean to imply that it's linear, it's more than likely curved. But it gives me a general sense of the direction of the graph just by plugging in numbers near 5. Moving on to the y-intercept, when we plug 0 into the function, we get a value of negative 5/3. So I've placed that there. Don't worry about scaling. Moving on to vertical asymptotes. Vertical asymptotes occur when denominators are 0. Clearly 9 is a solution to this problem, and therefore we have a vertical asymptote at 9. And so in my normal tradition, I'm going to plug in a number slightly to the left of that and slightly to the right of that to give me the direction that the graph is approaching the asymptote. In this case, because I got a positive on the left and a negative on the right, the graph must be approaching the asymptote towards positive infinity on the left and negative infinity on the right. If you need to pause and convince yourself why those quantities are positive and negative, now wouldn't be a bad time to do that. So on to the fourth component of the graph, the left end behavior. I like to plug in negative 1,000 to see what's happening to the graph at the far left end, But you'll notice this involves radical negative 1,000, and that's not a real number and therefore not of interest to us in graphing. As a matter of fact, you can see by looking at the original function in the upper right corner that if x is any negative number whatsoever, this graph doesn't have a real solution for y. And so there is no negative half of this graph in the x sense. So finally, let's look at the right-end behavior. This one's a little tricky, but I do like to plug in 1,000 just to give myself a sense of what's happening to this graph on the far right side. Notice the numerator is 995, or approximately 1,000. And what's happening in the denominator? Well, first of all, it's negative. The square root of 1,000 is probably around 30-ish. After all, 30 squared is 900. And so 3 minus 30-ish is going to be negative. But something else is happening here. While it is true that I'm getting a positive divided by a negative, one can see that the numerator is a lot bigger than the denominator would be because of the radical in the denominator. Imagine plugging 1,000,000 instead of 1,000. Your denominator would grow, but your numerator would grow faster. And if you were to work a few of these out by hand, you would convince yourself that this quantity is getting more and more negative as x gets bigger and bigger. The conclusion, therefore, is that as x approaches infinity on the right, y must be approaching negative infinity. Again, it's a tricky logic there, but both the numerator and the denominator involve the number 1,000, or 1,000,000 if you want to consider it at the next level. But the numerator will be so much bigger than the denominator because the denominator will be radicaling that huge number. That's my logic why y should approach negative infinity. What does that look like graphically? That means on the far right side of the graph, it's getting lower and lower and lower without lower bound forever and ever. So I've completed the 5 essential elements of the graph, and now it's just a matter of connecting them all up to get a rough sense of what the graph looks like. Now again, I've used a computer program to do this, so yours may not necessarily look exactly the same, but as long as yours has the same key features, and I'll point them all out to you, nothing left of 0, a y-intercept of negative 5/3, an x-intercept of 5, the graph approaching the asymptote of 9 as shown on both sides, and then the graph getting smaller towards the right, or lower, then you've correctly sketched this function, even if it doesn't look exactly like this. Now let's take a look at another function, this one involving a natural logarithm. Starting with our x-intercepts. X-intercepts occur whenever the function is 0, and solving this equation will show that e is the x-intercept for this particular function. So, to see the behavior near e, let's plug in a number slightly to the left of e, which is 2.7-ish. Now, it may seem strange to do this without a calculator, but it's doable, at least in terms of determining whether this is positive or negative. You see, the natural log of e is 1. Therefore, the natural log of 2.6, which is less than e, has to be less than 1. So what do we have here? We have 1 minus a number less than 1. 1 minus a number less than 1 has to be positive. Now that I've plugged in a number slightly to the left of e, let's plug in 2.8 slightly to the right. This quantity has to be negative. Reason? 2.8 is bigger than e. The natural log of e is 1, therefore the natural log of 2.8 is bigger than 1. So what I have here is 1 minus a number bigger than 1. 1 minus a number bigger than 1 is negative. So the positive and negative tell me the behavior of the graph near E, specifically that it will be above and then below the x-axis as shown. Y-intercept. Y-intercepts occur when x is 0, but the natural log of 0 doesn't exist, therefore there's no y-intercept of this function. Vertical asymptotes occur whenever the argument of a logarithm is 0, and therefore, because the argument is x equals 0 will be a vertical asymptote. By the way, x equals 0 is the y-axis. So I have a vertical asymptote there. Let's analyze the behavior on the left and right side of that asymptote. First, let's plug in a number slightly to the left of it, but the natural log of a negative doesn't exist. In fact, not only is there no behavior slightly to the left of this asymptote, you can see that there'd be no points to the left of that asymptote at all, because if x is any negative number, this function isn't real, and therefore it's not graphable in the sense that we care about. Now we'll plug in a number slightly to the right of 0, and what I've got here is the natural log of 0.1. That's going to be a number between 0 and 1. I'm sorry, the natural log of 0.1 is going to be a negative number. What I've got here is 1 minus a negative number. 1 minus a negative number is the same as 1 plus a positive number, which is positive. And because the y value is positive, the graph has to be approaching the asymptote in an upward direction. Think of it another way. If x is 0.1, y is some positive number. Therefore, this graph must contain the point 0.1, comma, positive. Where is that? Well, it's somewhere up there. And that proves that the asymptote is approaching, the graph is approaching the asymptote in that fashion. It's worth noting before we go on to left-end behavior that when an axis is an asymptote, we don't draw a dotted line over it. It seems unnecessary to clutter the graph with that kind of information. Simply look at the positive y-axis here. Simply drawing the graph near that, as we did, is an indication to the reader that the graph is approaching that line. It would be silly to draw a dotted line there as well. As far as left-end behavior goes, there isn't any. In fact, we've already determined that this graph doesn't appear anywhere to the left of x equals 0. And so there's no sense in analyzing the left-end behavior. But as far as the right-end behavior goes, imagine x being 1,000. Now, I mentioned earlier that the natural log of 1,000 is about 7-ish. You wouldn't necessarily know that, and I used a calculator on that. But imagine this, 1 minus 7-ish is about negative 6. So this graph passes through the point 1,000, negative 6. Imagine where that is. But furthermore, recall that the bigger x gets, the bigger the natural log gets. So if we were to plug in 1,000,000 instead of 1,000, we would have 1 minus a bigger number. If we were then to plug in 1,000,000,000, we would have 1 minus an even bigger number. And we would have 1 minus progressively larger and larger numbers, and therefore this function is going to get more and more negative as x becomes more and more positive. My conclusion, therefore, is that the y values are going to approach negative infinity, and therefore I'm going to draw my graph going that way. And with the 5 characteristics analyzed, all I have to do now is connect my graph in some logical way, and I've now graphed y equals 1 minus the natural log of x. So on to our 5th and final example of graphing without a calculator. X-intercepts of a fraction occur when the numerator is 0, therefore 1 is an x-intercept. plugging in a number just to the left of 1 will tell me, and to the right of 1 in a moment, will tell me the behavior near 1. Well, let's analyze this fraction here. The top is negative. The bottom is going to be a negative number as well, and therefore this is going to be a positive quantity. Why is the bottom negative? Well, e to the 0 power is 1. E is an increasing function, so e to the something bigger than 0 is bigger than 1. So what my denominator really is 1 minus something bigger than 1. 1 minus something bigger than 1 is negative, and therefore I have a negative divided by a negative here, which is positive. Now let's go slightly to the right of our x-intercept, and notice by the same logic the denominator is going to be negative, but this time the numerator is positive. So I've got a positive divided by a negative, which is a negative. And the positive and negative nature of the y values here, both to the left and right of the intercept respectively, tell us that the graph is going to be above on the left and below on the right. Y-intercept is found by plugging in 0 for x. If you work this out, you should get that it doesn't exist. Why? Because the denominator is 1 minus 1, or 0. So when x is 0, the function doesn't exist, and therefore there's no y-intercept. Vertical asymptotes occur when your denominator is 0, and that occurs when x is 0, as we just discovered attempting to find the y-intercept. So that tells me that I have a vertical asymptote at x equals 0. I'll erase that in a minute because it doesn't make sense to have a dotted line over the y-axis, but just for visual clarity for the moment, that is the vertical asymptote. So let's plug in numbers on either side of that because we want to know the behavior of the graph on either side of this asymptote. We'll start with something slightly less than 0. This turns out to be a negative quantity. Here's the logic. The numerator is negative. The denominator, let's analyze that. E to the 0 is 1, therefore e to the something less than 0 has to be less than 1. So the exponential we see in the denominator is less than 1. 1 minus something less than 1 is positive, therefore my denominator is positive. Overall then I have a negative divided by a positive, which is a negative. And if the y value is negative, slightly left of 0, then I must be approaching the asymptote that way on the left side. Now, slightly to the right of 0. The top is still a negative number, but the bottom turns out to be a negative number as well. So what I have here is a negative divided by a negative, which is a positive. Why is the denominator negative? Follow this logic. E to the 0 is 1. Therefore, e to the something slightly bigger than 0 is slightly bigger than 1. So my denominator is 1 minus something slightly bigger than 1. 1 minus something bigger than 1 is negative, and hence the denominator is negative and the overall quantity positive. The fact that I have a positive y value when x is 0.1 means that my graph must be up here and therefore approaching the asymptote in an upward fashion as shown. Now let's take a look at the end behavior on the left side of this graph. First we'll plug in negative 1,000. My conclusion, based on this calculation, even without a calculator, is that y has to be approaching negative infinity. Here's the logic. Notice the e to the negative 1,000 in my denominator. E to the negative 1,000 is approximately 0.00000000 something. It's some incredibly small, close to zero number, because if e to the 1,000 is gigantic, e to the negative 1,000 is 1 over gigantic. That's very close to zero. So my denominator has 1 minus something incredibly small. I imagine the denominator is about 0.99999, and therefore it's basically close to 1. And as x continues to get more and more negative on our left-hand behavior, that denominator is going to stay roughly stationary at about 0.99999. The numerator, however, is going to continue to be more and more negative. So what I've got here, if I'm plugging in 1,000, but I'm imagining it getting bigger and bigger into the negative, so to speak. And what's happening here is that as x gets closer and closer to negative infinity, the numerator continues to grow and be more and more negative, and the denominator is stationary right at or about 1. Therefore, the more negative x is, the more negative y is, and hence my graph is approaching negative infinity. What does that mean graphically? Well, it must be going downward in that direction. It's not linear, but that arrow gives a general direction of the graph. Now, as far as the right end behavior goes, let's plug in positive 1,000. My conclusion here is that the number that you're looking at right there, even without a calculator, has got to be very, very close to 0. Why is that? Here we have e to the positive 1,000. E to the 1,000 is probably too big for a calculator. I'm holding a calculator now. E to the 1,000th power. Too big for the calculator to handle. It's in the trillions of trillions of trillions and so on. It's an unimaginably large number. So what's 1 minus a trillion trillion trillion? Well, it's a very big negative number. So that's what I know about my denominator. So the bigger x gets, imagine that 1,000 were to change into a million. The denominator would become so huge compared to the numerator that we'd be doing a number divided by a number way larger than that. And when you divide a number by a gigantic number, you get something really close to 0. And therefore, my logic is that y must be approaching 0. And that tells me that the graph has to look like this. So we've got 0 as a horizontal asymptote, which again, to avoid confusion, we won't draw. So after all the clues are put together, all I have to do now is connect the graph up, and I'm done. This is probably the most challenging of all 5, and it sort of illustrates the point that graphing without a calculator can be a little bit of mental work. Now, it's worth noting that I've given you some general guidelines here, but you don't have to follow them. These aren't specific rules. They're great strategies. But ultimately, if this video was confusing to you, then let's not forget what our end goal is. When you're given a function, it comes down to one question. You're trying to give a graphic representation of what's happening to y as x sweeps across the real number line from negative infinity to infinity. Any way that your brain can do that, as long as it does it correctly, will give a rough sketch of the graph. You're not required to follow any of the steps that you've seen in this video, as long as your brain correctly pieces the graph together in a way that's logical to you. So don't feel constrained by my 5 key element process. Although, with that being said, it's worth noting that the key elements of the graph are what are being sought after. So I'm not suggesting that if you don't feel like finding the x-intercepts, you don't have to, or if you don't want to find vertical asymptotes, you don't have to. That's not what I'm saying. What I'm saying is, if you don't feel like analyzing the graph in the same way that I do, but you still come to the same conclusion where the vertical asymptotes and intercepts and end behavior would be, then that's fine, and that's all that matters. And that completes this video. Thank you so much for watching.